This video is on a very important concept involved with chemical equilibrium, which is called Le Chatelier's principle. Okay, so in a nutshell, Le Chatelier's principle says the following. It says that when a stress or a change, they're one and the same. When some stress or change in conditions is imposed on a system at equilibrium, the system or the equilibrium will shift to offset or oppose that change. I guess I need a little end quote there. Okay, so Le Chatelier's principle is basically like what you may have heard of in the past as a negative feedback structure. If you impose a change, Le Chatelier's principle says that a chemical system at equilibrium will try and offset that change to minimize the impact of the change. And what it means by a shift is it suggests that maybe the equilibrium was in one position, maybe it favored the products but had some reactants. When it shifts, it suggests that now maybe there are less products than there used to be and more reactants, or maybe even more products than there used to be and less reactants, but a new equilibrium will be established. So this is just a new equilibrium position, and it's not like when you stress an equilibrium, a system at equilibrium, it leaves equilibrium and never goes back. It will go back. It'll just go back to a new equilibrium position. Okay, and we call that a shift when that happens. Okay, so to demonstrate or illustrate how different stresses or different changes to conditions will impact or will shift an equilibrium, I'm going to use the example here of a very famous system that exists in equilibrium called the Haber process. Okay, so this is called the Haber process, and what we see is that we have ammonia over here, okay, which is a gas. All of the reagents and products here are gases, and it is made of atmospheric nitrogen, or by reacting atmospheric nitrogen with hydrogen gas, okay. We can also see that this is an exothermic process in the forward direction because we can see that energy is released, all right? So what we can evaluate are different factors, and the factors we'll explore are concentration. So we'll see how impacting the concentration of one of the reagents can shift the reaction. We will also look at the pressure or the volume of the system, okay? So, of systems involving gas, like this one, involving gas. And thirdly, we will look at temperature, okay? So what happens if we change temperature, okay? So let's look at concentration first of all. I would like you to consider this. If we increase the concentration of one of these reactants, let's go ahead and just say, hydrogen, okay? Let's say we increase the concentration of hydrogen. What can the system do to offset that change in concentration? I want you to pause the video for a second and consider that. Okay, hopefully you took a minute to think about that. So if we all of a sudden increase the concentration of hydrogen, what we would expect to happen is we would expect a shift to the right. Okay, a shift to the right. Why would we expect that? Well, because the main thing Le Chatelier's principle says a system at equilibrium tries to do to offset a change is to do the opposite of what happens. So if this system increases something that's on the left, it wants to shift to the right to use that up, okay? So in the process, what would happen would be that nitrogen would end up going down a little bit because some of that's getting used up to react the hydrogen, and we would see that the ammonia would go up. We would also see the temperature go up because it would release energy. Okay, so there's a lot of knock-on effects with Le Chatelier's principle. When in terms of pressure and volume of systems involving a gas, if we increase the pressure of the system, Or, exact same thing as that, it would be decreasing the volume because of the way volume and pressure are related. If you think about it, when you decrease volume, you increase pressure, or when you increase volume, you decrease pressure. So let's say we're going to increase pressure by decreasing volume. What do you predict would happen for this system at equilibrium? Pause the video for a minute, look at the gas molecules, and make a prediction. Okay, I'm going to use the green pen to discuss this one so you can tell that these are the all the changes involved in green have to do with the pressure factor. Okay, so let's imagine that we are going to increase the pressure. Look at the gas molecules to figure out which way the system is going to shift in response. If we look here, we have one gas molecule here, okay, for nitrogen, and we have 3 there for hydrogen. That's a total of 4 gas molecules on the left. If we look here, we have 2 gas molecules on the right. All right, so in other words, if we increase pressure, what wants to happen is it will shift to the side with fewer gas molecules. It shifts to fewer gas molecules. And that's because we generally regard any gas molecules as occupying the same amount of space. And so if we can force the system into a condition where there are fewer gas molecules, those will occupy less space. And so if you increase pressure, it shifts to the side with fewer gas molecules, which means it is going to shift to the right again. Shifts to the right. Okay, I promise I didn't plan them to all shift to the right, just coming up with this. Finally, and I'll use red for this one, what would happen if we increased the temperature of this system? Pause the video, look at where the energy is, and make a prediction. Okay, if we increase the temperature of the system, we basically have to look at where is the energy factor, and the energy factor is here. So if we ramp that up, you can kind of treat it like the concentration effect. If we're increasing the temperature, what it means we're kind of increasing the energy, and the whole system is going to shift away from that, okay, to try and offset it and try and use that energy. So what would happen if we increase the temperature of this reaction, because it's exothermic in the forward direction, is it would shift to the left. It shifts to the left to offset that change, okay? Now hopefully this makes sense. If you're not sure, go back and realize that for Le Chatelier's principle, it always tries to offset the change imposed. It can be really handy and convenient to look at graphs of how the concentration changes for each of the respective reactants and products over time for a system at equilibrium. So let's try and model this with a concentration, basically concentration time graph for what would happen for the scenarios we just talked about. So for the concentration one, we said, let's increase the concentration. So let's say at time X, we increase the concentration of hydrogen. We would just see that go whoop. Then what would happen? We said it would then shift to the right. So that means hydrogen's going to immediately be consumed. So it's going to start going down. We would also see the nitrogen then go down as well, okay, until it leveled off, And what would we see with the ammonia here? We would see it actually increase until it leveled off, okay? So in response to that, and my graph isn't perfect, but eventually it would reach the new equilibrium position again, and that would be once they all flattened out again. Okay, so this is your shifted, your new equilibrium is established once they're flattened again. Okay, so again, this is a sketch, pardon the sort of rudimentary nature of the whole thing, but let's look at the pressure effect, okay, like we did. And, oh gosh, what did we say? Yeah, we said we were going to increase pressure. Okay, so again, this is if we go ahead and increase pressure. And we're going to increase it right here at this moment right there. And we said if we increase pressure, it was going to shift the whole thing to the right, okay? And that's because there were fewer gas molecules here. There's only 2 gas molecules over there, and there's 4 over here. so we know it's going to shift to the right. So what we need to show in the concentration versus time graph is we would show a decrease at that time for hydrogen. We would show a decrease, although I'm trying to do it on a 3-to-1 ratio. See, for every like 3 moles of hydrogen went down, we'd go down by 1. So then I should show the nitrogen going down, about a third as much. And then we should show the ammonia going up, about twice as much. So it might even go up like that, something like this. It's probably not perfect, but then your new equilibrium is established here, okay, in response to that. Okay, and then finally the temperature effect. Oh, I forgot to put my little starting point on there. I don't know, H2. These are arbitrary, by the way, like what the actual concentrations were at the start. I'm just putting them on. Okay, so for temperature effect, we said that we were going to increase temperature, yeah? Okay, we're going to increase the temperature. And then we said, well, basically that's like increasing this. And so basically the thing is going to shift to the left. Okay, so when we impose the change or the stress of increasing temperature at time x, what we should see is a decrease in NH3, and it'll establish a new equilibrium. And we're going to see an increase in N2, and we're going to see an increase in H2 as well. Okay, and so at this point when they're flat again, that's your new equilibrium position, okay? Or in other words, the system has shifted. Hopefully that makes sense.